Hello everyone, today is the day 16 of 75 hard research challenge. I'm going to talk about what I did yesterday, that is on day 15. I studied retrieval augmented generation, or famously known as RAG. Specifically, I studied how to use vector databases and what is approximate nearest neighbor search. So let's get started. So in the case of retrieval augmented generation, what people saw is that when we use large language models to generate text, they often fail to generate very correct factual text, right? For example, if you say that where does Barack Obama lives, then they may be able to say that he lives in United States, right? But if he has recently changed his location to, let's say, some other state in the US or some other city, and it has the news has gone viral, then the large language model will not know about it. The primary reason for that is that it has been trained on data that has not seen the change in the training set. One second, even if you give it the training set, it is not feasible to retrain the model every month for every person possible, right? So how do you go about it? The easiest solution for this would be to have a large language model and that can access, right, some form of database, right, and generate its response based on that, right? So the facts being generated or facts being used by the large language models are grounded in reality using the database, and you keep on updating the database very frequently, which is much cheaper as compared to fine tuning a large language model, right? So this is where retrieval augmented generation comes into picture. Generation, because large language models are being used to generate text, and retrieval augmented simply means that you're using some form of data set, database, or set of documents or web pages, things of that sort, right? Or maybe even logs in case of, let's say, you're building a system for monitoring error stacks of code, or network management, etc., right? So how do we go about it? How do we build such a system? So let's say you have a set of documents, web pages, and text sources with you. Because large language models have limited context window, you have to divide these documents into chunks, right? So you take these documents and you divide them into chunks. Once you have divided them into chunks, you pass them through some form of sentence embedder to embed each of these chunks, right? And this is a, you can use a pre-trained model for this. You don't have to fine tune this or train it, or do anything. This is, the red box is essentially a pre-processing step for RAG, right? So once you have divided into chunks and gotten sentence embeddings from, or chunk embeddings from but let's say BERT, you put it into something called a vector database. Vector database is nothing but a database specialized for storing some form of numbers and embeddings, right? It has been there in the past, and people are just using it out of the box, coming from other applications, right? So let's say you have done this, you have processed and got an embedding for each of your document. Then what do? You simply do that. Let's say your user gives you a query, you use the same sentence embedder, right, and to process the query, you get the query embedding. Now what you do is that you pass this query embedding to the vector database, and it will match each of the entry in the vector database using some form of algorithm that we will see with the query embedding, right? And it will return top k responses that it has. Once you have the top k responses, you can concatenate the top k responses as a prompt with the query and pass it through the LLM. The LLM will now generate a response. Earlier, what we would have done in the case of not having this RAG model is that we would have passed the query directly as a prompt to the LLM, and we have gotten the response, right? So this is a basic understanding of RAG. There is no fancy things around it. There's only some code involved in this. I will be releasing a video soon. But let's first see that how this particular step happens, right? How do you search a particular embedding query embedding in the vector database? Okay. So one of the naive way would be to compare each entry in the data set with the query embedding and return the top k, right? And this will require order of size of vector database times the d dimension embedding that you have, right? So it is very naive and it is not scalable. So what people have come up with something called hierarchical navigable small worlds, or HNSW. So they trade precision for speed. Okay, so they use something called approximate nearest neighbor search. Let's go through this. Okay, so how do you search in a vector database? You take as input an ANN graph. Let's say these embeddings are not stored linearly as in a traditional RDBMS. They are, let's say, they are stored in the form of a graph. Okay, we will see that how this graph is being made, but let's for now focus that we have a graph of the sort where we have a node for each embedding, embedding 1, embedding 2, embedding 3, embedding 4, let's say, and these are connected to each other using some edges. How do we define these edges? We will come to it later, but let's assume someone has given it to us, right? So we have an ANN graph, approximate nearest neighbor graph, and a query to search. Okay, the output will be top k nearest neighbors approximately. So we are going to repeat m times, where m is a parameter. We start with a random input node. Okay, let's say we start with E4 in this case. Okay, so we match the similarity with it and its neighbors. So we match the similarity of our query q. Let's say we have a query q with us. So we match the similarity of q and E4. Then we match the similarity of q and E3 and the similarity of q and E1. Okay, now if the similarity score of E4 with Q is higher than each of E4's neighbors, then we stop this particular search. Okay, and we say that E4 so far we just simply stop the search. Okay, but if let's say for some reason E3 has a higher similarity than E4, then we shift to E3. Okay, we keep note of E4 and E3 both. Now what we will do, so that's what I have written, that move to node with higher similarity. Then we stop it if no more neighbors have higher similarity. Okay, let's say the neighbors of E3 are E1 and E4. So E4 we have already tried and we know that similarity measure of E3 is greater than E4. So we check whether E1 similarity is better than E3. Let's say it is not, then we stop this search and we repeat this process m number of times. Okay, now we have, after these m number of times we have evaluated this particular set of statements, what we have left with is a sequence of or a set of nodes that we have visited. For example, let's say we have visited E3, E4, E1, and then let's say E5, E20, E21 or something that sort. Next, we also have the similarity scores of all these nodes with Q. So we pick the top k similar nodes among all visited. Okay, so that's all we do to search in a existing approximate nearest neighbor graph. Okay, so what was the solution? Solution was simple, that rather than storing linearly in a vector database, you store it in the form of a graph. Okay, how do we insert in this particular graph is an open question, and let's address that. So in order to insert a particular node in a graph, we do the same thing again, that let's say we want to insert q in this graph. Okay, so how do we go about it? We start from a random node. Again, we continue doing the search. We repeat this particular search. We get the top k similar nodes, and simply we insert the node in the graph and connect. Let's say we inserted q, then we connect. Let's say top k is equal to 2 and k is equal to 2, and it came out to be E1 and let's say E3. Then we connect q to E3 and q to E1, and that's it. That's our new updated graph. Okay, so search is a key part in insertion as well as, of course, querying this particular graph, this vector database graph. Okay, so that's all for today. I'll be releasing a code video, but unfortunately I'm not able to get access to a GPU for some reasons, so please wait for it. Thanks.